So you'll notice the difference between this one and the section before it. The section before it was using identities to simplify. So either you're given one thing and they want you to find other things, or you give this really big kind of statement and they want you to narrow it down to a much smaller, more simplified statement. And like I said, the biggest problem with that is some people are like, do I keep going or am I done? What's going on here? Typically in those, if you end up with some crazy fraction of a trig problem, you're probably not done because you have some reciprocal identities and quotient identities that you can simplify out. With these, what's nice about them is you are verifying it. It is actually saying these two equal each other. Now prove it. So when they say prove it, they want you to actually get to some point where you see that they're the same exact thing. For something like this, I would take the most difficult side and try to get him simplified to look like the other side, depending on, which one's the simplest one. Clearly, the left side is the more difficult one here, right? So if I can just get the left side to be cosecant squared, then I have proven that those are the same, right? And so that's what I'm going to do. Now, anytime you see a squared, hopefully your brain is going to that handout that I gave you and you're going to Pythagorean identities, right? And so tangent squared plus 1 is a written identity exactly the way you were given it. What does tangent squared plus 1 equal? Yeah, so we're going to replace the tangent squared plus 1 with secant squared. And that's going to be over tangent squared. Now at this point, there is nothing that those two together just naturally reduce. So I would then convert to sine and cosine here. All right. And so if I convert secant to sine or cosine, that's going to be 1 over my cosine squared. And if I have tangent squared, that's going to be sine squared over cosine squared. Now, keep change flip here because it's a fraction over a fraction and they're the same denominator. My denominators are going to cancel and I'm going to end with numerator over numerator, right? Keep change flip is going to cancel those denominators. And I am going to end up with something that looks like this. 1 over sine squared of x. And I noticed I changed it from theta to x, but that's okay. That is a reciprocal identity that we know. What's the reciprocal of sine squared? Cosecant squared, and I am done. Okay, so I'm done with that because I know where I was headed. So I take the most difficult side and I simplify it. That's the goal of these verifying. So this is when we're going to have to get a common denominator. My common denominator is just multiplying the two of those. So I'm going to leave that left side completely alone, and I'm going to manipulate the right side. My common denominator is going to be the two of those multiplied, sine x plus 1, sine x minus 1. That is my common denominator. I need to multiply the left guy by the sine x minus 1. Pay attention to your negatives here because that's where people mess up. I need to multiply the right side by the sine x plus 1, right? My denominator here is conjugates, right? A plus b, a minus b, yes? So what happens when I multiply conjugates? It becomes the first one squared minus the second one squared. So that denominator actually simplifies to sine squared x minus 1. The numerator, I have sine x minus 1, distribute that, minus sine x minus 1, right? Distribute that negative. You'll notice those sine x's cancel, right? Anything minus itself is zeros out. Negative 1 minus 1 is negative 2. So I have negative 2 over, and sine squared x minus 1 should trigger a Pythagorean identity, right? Not an exact one, but sine squared plus cosine squared equals 1. If I want sine squared minus 1, move the 1 over, move the cosine over, right? So I can replace sine squared minus 1 with negative cosine squared of x. Negative over negative, those cancel, right? And what is the reciprocal of cosine if I want to put him up there? Well, that's just going to be secant. And I'm done. So this is using factoring, but this is kind of a weird way to use factoring. Honestly, it doesn't matter which side you simplify. You're going to actually do the same exact process. They simplified the right side, so I'll do it so you can follow along in your book. But really, the process of doing this, it doesn't matter if you do the left or the right. You're going to get to the same concept either way. So they just left the left side alone, and they said, let's factor the right side. Well, when you factor it, I have tangent to the fourth and tangent squared. So factoring tells me I can take out a tangent squared. So that's what I'm going to do. And I'm going to say, pull out a tangent squared. I'm left with tangent squared here plus 1. And that should really look like something familiar, right? I can actually rewrite both of these using Pythagorean identities, okay? Tangent squared plus 1, that is the same thing as secant squared. All right, so I can replace this guy with secant squared, right? And tangent squared is the same thing as secant squared minus 1, right? Everybody agree with that? Tangent squared plus 1 equals secant, so secant squared minus 1 equals tangent. So I'm going to replace this guy with secant squared minus 1. Well, I now have two things being multiplied, so I can just distribute, right? Secant squared times secant squared is secant to the fourth. Secant squared times negative 1 is negative secant squared. And that's the same thing. And I could have done that over here. I could have pulled a secant squared out, and I would have had secant squared minus 1. Well, that's tangent squared, and I could have replaced secant squared with tangent squared plus 1, distributed, and I would have gotten tangent to the fourth plus tangent squared. So either way, you could have done those. So when you have a secant on one side and a tangent on the other, you're likely going to use Pythagorean identities when you pair them up like that. conjugates you're going to see over and over because conjugates lend itself to Pythagorean identities here. And so I'm going to leave the right side alone, and I'm going to say, well, I really have nothing I can do here, except I do have a cosecant plus 1. So I can use cosecant minus 1 here. Multiply the top and the bottom by that conjugate. Right? We have cotangent x, cosecant x minus 1 on top. And then cosecant plus 1, cosecant minus 1 is cosecant squared minus 1. All right? Which should look like a Pythagorean identity. 1 plus cotangent squared is cosecant squared. Right? So if I subtract the 1 over, then cosecant squared minus 1 is just cotangent squared. And so I have cotangent x over cotangent squared. And I can cancel out one of those cotangents, and I'm going to do exactly what I did before. I have a binomial on top. I'm going to split it up, keeping my denominator. So I'm going to say cosecant x over cotangent of x minus 1 over cotangent of x. All right. Let's look at just that guy, okay? Cosecant is 1 over what? 1 over sine, right? Cotangent is cosine over sine. So this guy simplifies to 1 over cosine, right? Which is what? 1 over cosine is secant of x minus cotangent of x. So if you went from here to here, I would need you to show me that piece of it to the side. Okay? Because there is no identity that says cosecant over cotangent is secant, by the way. So when you go through these, you're going to start with the easiest. If I can simplify one side, go there. If I can substitute with Pythagorean identities, go there. Maybe I need to multiply conjugates. So you're obviously going to do the path of least resistance and work your way up. There is going to be a time when you might say, they're both complicated. Let me simplify both of them and see if I can work them out to the same. And that is a valid way to verify them as well.